Hello class, welcome to Geometry Lesson 4.5. We're going to talk about congruence in right triangles. So the essential question today is what minimum criteria are needed to show that right triangles are congruent? So the learning goal for today is to be able to identify congruent right triangles. So we're going to talk about various triangle types based off of the angles of the interior. So for example, an acute triangle is a triangle with the interior angles being acute angles, meaning that they're less than 90 degrees. So if we have on the right an example of an acute triangle, so I'll notice that all these angles are less than 90 degrees. The next type of triangle by type is the obtuse triangle, which has only one interior angle that is an obtuse angle, meaning an angle that is greater than 90 degrees. And so in this case, we have an obtuse angle, which is the 100 degree angle. And the last type of triangle is the right triangle, which has one interior angle that is a right angle. And notice that the rest are acute angles. And so remember that all the angles in a triangle have to add up to 180. And so for acute triangles, all of them are acute. For obtuse triangles, one of them is obtuse. For right triangles, one of them is a right triangle. But then notice that the other angles are going to be acute angles here. And so the triangle that we're going to be focusing on today is the right triangle. And so let's go ahead and remind ourselves about right triangles. So remember that a right triangle, as we mentioned earlier, has a 90-degree angle. And the longest side of a right triangle is called the hypotenuse. So that's the longest side in a right triangle. And then the other sides in a right triangle are known as legs. And so just the basic anatomy of a right triangle. And remember that the famous theorem for right triangles is known as the Pythagorean theorem, and it relates the side lengths, the legs, to the hypotenuse. And so remember that the Pythagorean theorem states that, well, if you have a right triangle, then the sum of the squares of the legs, when you add, of the legs, is equal to the square of the length of the hypotenuse. So a squared plus b squared equals c squared. And I know a lot of you guys remember this, but not everybody is, well acquainted with this theorem. So I want to make sure that everybody's on the same page. And so whenever you think of a right triangle, a lot of people tend to think of this theorem. All right, so how can we show that two right triangles are congruent? So if we want to investigate right triangle congruence here. So if we have two right triangles, like in the diagram given below, if both pairs of corresponding legs are congruent, then we can use SAS. Remember, SAS stands for side angle side, with AC being congruent to DF and C being congruent to F, because C and F are, in this example, they're right angles. Let's go ahead and label those here real quick. So these are 90 degrees, and so they're congruent. Remember that all right angles are congruent, and we know that AC is congruent to DF, and based off of this diagram, BC is congruent to EF. And so if we have something like this, right? If we have both pairs of corresponding legs are congruent, then we know by SAS that these two triangles are congruent. So that's one case in which we know that two right triangles are congruent, if we have SAS. Another case in which we can determine that two right triangles are congruent is with the use of the Pythagorean theorem. So if we know one of the sides, so if we have, for example, in this case, we have AC, and we know that that's congruent to DF, and obviously it's a right angle, and so we know that this angle is always going to be the same for right triangles. So we know that, and let's say we know the hypotenuse, right? So basically we know two sides for each triangle, and we know that they're congruent. Well then, even though we can't use SAS here, we can actually show that these two triangles are congruent because we know what the third side is. Because remember, by the Pythagorean theorem, if we know one of the legs is, for example, A, which could be a number like 5 or something like that, and if we know that the hypotenuse is C, C is always reserved for the hypotenuse, by the way, well then we can figure out the other leg, B, right? Because remember that by the Pythagorean theorem, A squared plus B squared equals C squared. And so I can solve, if I know C and B, then let's just say I know both of these, so I'll box them because I know them. Well, then I can solve for B squared by subtracting A squared on both sides. And so if I do that, well, then I get b squared equals c squared minus a squared. And since I know c and a, I really know what b is. And in order to find b, I would just take the square root to get the other guy. Because remember, the only way to get rid of this square is by doing a square root. So, because remember, the square root of b squared, they cancel. And so in order to get b, I could just take the square root of c squared minus a squared. And so if we know the hypotenuse and we know one of the legs, then we know that the two triangles are congruent because we can figure out the other side. And when we figure out the other side, we'll end up being able to use SAS, right? So if we know that this side is the same, then we can claim SAS. All right, so let's go over another scenario. If we have two right triangles that are congruent, or two right triangles, are they congruent if you have one pair of corresponding acute angles and one pair of sides? Can we determine if the triangles are congruent? And the answer is yes, we can determine that they're congruent. So look at this first case. We have one pair of acute angles, which are these angles right here, B and angle B and B prime. And we also know that because it's a right triangle, we know that the right angles are congruent. And so we have a pair of congruent angles for B and C, and we know a side. So let's say we knew this side. Well, then we can determine that these are congruent because they're congruent by AAS, right? So this is angle, angle, side. And so we can determine that these are indeed congruent by AAS. All right, now the other case is, well, let's say we know A instead of B. Well, then if we know A is congruent to A prime, well, then now we have another pair of angles, right? So we have angle, an angle, and let's say we know this side. We can also determine that these two triangles are congruent. How? Well, they're congruent by ASA because we have an angle, side, and angle. Okay, so we can determine if two right triangles are congruent by these cases as well. And so basically we've introduced 4 cases for investigating right triangle congruence. Now let's go back to the other case that we dealt with. The case that we dealt with was for right triangle congruence if we knew the hypotenuse and one leg other than the hypotenuse for a right triangle, then they must be congruent. Why? Because we can determine the other angle using Pythagorean theorem, right? And so this theorem is known as the hypotenuse-leg theorem, meaning that if you have a hypotenuse and you have one of the legs, you can determine that the right triangle is congruent. So hence the hypotenuse-leg theorem. Okay, so can we conclude that the pair of triangles are congruent by the hypotenuse-leg theorem? So for A, we know the hypotenuse is 9. So that's going to be C. Remember that C is the hypotenuse, right? Generally, that's what we call it, is C. And also notice that sometimes when you have a triangle, even though we know that C is usually when you draw a right triangle, C is usually the hypotenuse, and then A and B are the legs. If you have a triangle like this, where you have L, M, and N, you have other letters, sometimes you'll see that the side that is opposite of the angle, that's the side with the lowercase letter. So we have a capital angle M. Sometimes they'll use a lowercase m here to indicate that that's the side that relates to angle M. And then similarly, we have a capital N here. So directly opposite to that is a lowercase n. And then directly opposite to the capital L, the angle L right here, is the lowercase l. And sometimes you may end up seeing letters that are like this, right? Lowercase letters for the sides and uppercase letters for the angles. Sometimes you'll see that, but not all the time. But just keep in mind that sometimes you'll see a diagram labeled as such. But in any case, we have the hypotenuse, which is 9, and we have the side here. So we don't have a hypotenuse, we got a leg. So we got a leg here, we got a hypotenuse here, and that's it. And so we cannot conclude that these two triangles are congruent because We don't know the leg of the first triangle. We don't know the hypotenuse of the other triangle. So we can't assume that we know this. Okay, so we can't conclude. So can't conclude by HL theorem. Now for B, we have a leg. So we'll call this L, and we have a hypotenuse. So leg, hypotenuse, so that's good. We have a leg, hypotenuse. Now this leg has to correspond to the leg on the other triangle. It can't just be any leg, right? So if you look at this triangle, well, this leg corresponds to the leg that is basically it's the leg that is sort of like opposite of the angle, like directly opposite, like this, kind of like this. So yes, this is the same triangle basically. So by the HL theorem, these two are congruent. Okay, so congruent by HL theorem. Now for C, we have a leg and a leg, a leg and a leg. So, and I didn't really mean to make that. I should have used L. So we have a leg and a leg, so no hypotenuse. And so we really can't conclude this by the HL theorem, technically speaking. However, by the Pythagorean theorem, we can actually determine what the hypotenuse is. And so technically you can conclude that these are congruent, but you can't use the HL theorem directly. Okay, so you can't use the HL theorem directly, but you can kind of use it indirectly, because we know the hypotenuse is 3 squared plus 4 squared equals c squared, and 3 squared is 9, 4 squared is 16, 4 times 4, and 9 plus 16 is 25, right? So what number multiplied by itself gives you 25? Well, that number is 5. 5 times 5 is 25. And so the hypotenuse here is 5. Same here, the hypotenuse is 5. And so then once you find this hypotenuse, then you can claim HL theorem, right? But you can't use it directly. And that's really what I was asking in this question is, can you use it directly? But technically, we can use it indirectly. So even though they're congruent, you can't conclude it by direct means. Okay, so therefore we say cannot conclude by HL theorem for the first one. And then for the second one, yes, by the HL theorem, they're congruent. And then for C, like we said, cannot conclude directly by the HL theorem, but indirectly, yes. All right, so example 2. We have, we want to be able to prove that triangle ABC is isosceles. So triangle ABC is this entire triangle here. We want to be able to prove that that's an isosceles triangle. Now, remember that this right here indicates that this side is congruent to this side. It's not saying that this whole side is congruent to this whole side. It's only talking about part of the side, not the entire side. So it's very deceiving, okay? So this is not an isosceles triangle just by looking at it. You have to actually prove that it's an isosceles triangle. All right, so let's go ahead and start with our 2-column chart. Remember that these statements, the first statement is always some kind of given statement. And in this example, I don't include all the given statements. I only include some of them. Okay, so the first, at least for the first statement, I don't include all of them. Now for the first statement, I include only half of the given statements. Later on, I incorporate the other given statements. Okay, so first given statement, FD is perpendicular to AB. So that's referring to this part. FD is perpendicular to AB, and that's why this is a right angle. Perpendicular means that you have a right angle, and so that's why we have that right angle there. And then FE is perpendicular to AC, which is why you have this right angle here. Okay, so that's a given. And so now because we know that they're perpendicular, well then that means that FDA is a right angle, which is equal to 90 degrees. And we also know that FEA is also 90 degrees, right? And we also know that FDB And I'll highlight this. We also know that FD, let's use another color here actually. We also know that FDB is also a right angle. Why? Because remember that 90 degrees and 90 degrees adds up to 180, and a straight line adds up to 180, and it's perpendicular, so we know it's going to be 90 degrees. Similarly, FEC is also 90 degrees. And because of that, that means they're equal to each other, which is why we say FDA is equal to FDB, FEA is equal to FEC. So really, they're all equal to each other. That's the definition of perpendicular angles. All right, and so because they're now equal to 90 degrees, we know that these are right triangles. And so we have triangle FEA is a right triangle, FDA is a right triangle, and then the two green ones are right triangles. Why? Because that's the definition of a right triangle. As I mentioned earlier, a right triangle has a 90-degree angle. And so the next step is, now that we know that those are right triangles, we can use some theorems involving right triangles. But first, what we want to do is incorporate the third given statement. AE is congruent to AD, and that's given. Why do we want to include that now? Well, the reason why we include that now, so if we highlight this, we know, let's use another color. So now we have AE is congruent to AD. And so the reason why we want to include that now is because we're going to start using one of the theorems, because we know that since these are the same, because that's given, we also know that AF is congruent to AF. That's a reflexive property because it's congruent to itself. And so we have another side right here, this side right here. And so because of that, we can actually use the HL theorem, because now we have a hypotenuse and we have a leg. And remember, by the HL theorem, if you have a hypotenuse and a leg in a right triangle, and the same thing for the other triangle, then that means those two triangles are congruent. And so by the HL theorem, FEA is congruent to FDA. And these are the two blue triangles. And similarly, we know that, and before we actually get to the other triangle, let's go ahead and continue with the green triangles now. Let's move on to the green triangles. So we know that these green triangles are right triangles, and we know that CF is congruent to FB based off of the tick marks here. But we also know that DF, or that EF is congruent to DF. So let's label that on here. So we know that EF is congruent to DF. And why do we do this? Well, because we need this for the green triangle, for the triangles on the bottom, these bottom left ones. But how do we know that they're congruent? Well, we know that they're congruent because we know that the blue triangles are congruent. And because the blue triangles are congruent, I can pick this statement off from here. EF is congruent to DF. I can pick it off that statement. Remember, when we pick up many statements from the original congruence statement, that's called CPCTC. It stands for corresponding parts of congruent triangles are congruent. We can pick that off straight from this statement number 6. Okay, so why do we do that? Well, because now we can incorporate the other given statement, which was that CF is congruent to BF, because that's given. And now we can claim that these bottom triangles are congruent by the HL theorem, because now we got a hypotenuse here and we have a leg here, the purple legs here. And therefore we can claim HL theorem. And so now we know that those two triangles are congruent. And so now that we know that those two triangles are congruent, we can use the CPCTC, corresponding pair of congruent triangles are congruent, to claim that finally, and let's use another color here, finally, we can claim that ECF, which is this angle right here, is congruent to DBF, this angle right here. And now that we know that those two angles are equal, we know that this is an isosceles triangle. Why? Because of the converse of the isosceles triangle theorem. Remember that if you have an isosceles triangle and you have two angles that are opposite that are, well, okay, so if you have a triangle with two angles that are opposite of each other that are congruent, right? These are congruent. Well, then that means that the opposite sides are congruent. And if the opposite sides are congruent, that means that it's an isosceles triangle. And this is the converse of the isosceles triangle theorem, is if you know that those two angles are congruent, then you know it has to be isosceles. And so based off of this, we know that because of that, that AC is congruent to AB. That's because of the converse of the isosceles triangle theorem. And then therefore, because those two sides are the same, then we can finally conclude that it's an isosceles triangle. Triangle ABC is isosceles. Why? Because that's the definition of an isosceles triangle. The definition of isosceles triangle is if you have two sides that are the same. And the proof is complete. So there's a lot of working parts to this. But hopefully by looking at this exercise, you can kind of get, it can kind of flex your muscles as far as, getting some practice and looking at the different tools that you can use to be able to prove theorems, right? There's a lot of properties that we used here. So this is a really good exercise in practicing those properties. All right, so let's look at another proof exercise. So we have JL is perpendicular to KM. Perpendicular means 90 degrees, right? And that's why we have this 90-degree angle here. So JL is perpendicular to KM, which is why we have that right angle. And then JK is congruent to LK, which is why we have this. All right, so if we want to prove this, well, let's go ahead and start with our given. Let's start with the perpendicular. So because it's perpendicular, it makes a 90-degree angle, which means that J and K and L and K are both right angles, right? They have to be right angles by the definition of perpendicular lines. And the next thing, because they're right angles, that means they must be congruent, right? Because these are both 90-degree angles. And so they have to be congruent. And why? The reason is because all right angles are congruent, regardless of how it looks like. If it's a right angle and then you have another right angle and you compare them, they're congruent. They're the same. And so now that we know that these are right angles, then what we want to do is we want to use some kind of, HL theorem or something like that, because these are right triangles, right? And so KN is congruent to KN is this side right here. So basically, because they share this side, we know that it has to be congruent to itself. That's the reflexive property. And so now we have a hypotenuse and a leg, and therefore we can use HL theorem. We know that these two triangles have to be congruent. We know that this triangle here has to be congruent to this triangle here by the HL theorem. We have a hypotenuse and a leg. All right, next we want to show that, well, because now we know that they're congruent, right? Now that we know that those two triangles are indeed congruent, well, then that means that JKN, this angle right here, is congruent to, let's choose another color here, is congruent to LKN. So those two have to be congruent. Why? Because of the CPCTC. Corresponding pairs of congruent triangles are congruent. Because we can pick that off from this statement right here. So directly from the statement, you can see, okay, well, angle J can be congruent to angle K, which is what we have here. Angle JKN is congruent to LKN. Okay, so that's by CPCTC. So now we know that these are congruent. And because they're congruent, we can go ahead and proceed from there. Eventually, we're going to be proving that another triangle is congruent. We're going to be using this in a little bit. So now the next thing we want to look at is, well, okay, so now we know that these two angles are congruent. We're basically looking at these big triangles now, this triangle and then this other triangle. So that's what we're looking at right now at this point. Okay, so now we're saying that KM is congruent to itself because these triangles share that side, right? And so that's the reflexive property. And now we can, using the other property that JK is congruent to LK, that's a given, right? So now we can say, okay, well, JK is congruent to LK, and using using these three things at side, angle, side, we can show that these two triangles, triangle 1, triangle 2, are congruent by side, angle, side, by that theorem. And so now we proved that they're congruent. End of proof. All right, guys, that is it for the lesson. I hope you learned something from this video. There's a lot going on with theorems, but hopefully you were able to learn something with the right triangles. And as usual, I'll see you in the next one.